we were doing Fourier Transform. Last time we finished 1D. So now we will move to 2D. In last class we started 1D transformation, right? And I spent lecture on it why other because basics. This is right? So it was necessary to, in order to go to 2D DFT or 2D Fourier Transform, we have to learn some part of it. Once we get used to that one, applying the same thing to 2D, okay, and that's why I opened both of them, 1D and 2D, so I can go back and forth to make things smooth. Okay. So in 1D, mostly what we did, we said that the filtering can be a part for 1D, okay, and the filtering, which is convolution, in the special domain is the Fourier simplification. And also we saw that Fourier transform, it helps us in finding out the sampling rate. Okay, so we have to actually, we did all these things for the 1D thing. That was not our target, okay? Our target is 2D, okay, again, but I have to go to 1D to have smooth transition. Let's see how 2D Fourier transform will look like. So if you remember 1D Fourier transform, or any Fourier transform, what it is doing, it is transforming a signal into sum of sine and cosine components. Okay. So the same thing, we expect the image should be decomposed into sine and cosine components. Okay. Anyhow, this is just a definition. The output transformation is called the Fourier or the frequency domain. One input is called special domain. Nothing new. And why we are doing this? Because it's been used in a lot of image processing applications such as image analysis, filtering, reconstruction, and compression. So some of them we will study in this course, and rest left. So similarly, as we have in the 1D, we started with the Fourier transform because the continuous domain. Then we move to DFT. Okay, and DFT is actually our target because the signals are discrete. Okay, so the signals are discrete, the DFT is the one that we have to use. And FFT is the algorithm to implement DFT to make the thing faster. Right? So FFT is nothing, but it's an implementation of DFT. Okay, okay. So again, if you remember, there was a very nice picture in which a signal is decomposed into some of sinusoids. Like for example, this one, then there's some other frequencies. Okay, and plus some other frequencies. So this is what is Fourier transform is doing. The signal is decomposed into sum of sinusoids. So how it will look like in image domain or the 2D? You have image, and this has been decomposed into various sinusoids. Okay, and here not only the frequency is changing, but if you see this frequency is same as this frequency, but it's shifted. So we have the phase information as well. We will see that the phase information is important. Okay, so basically our image is decomposed into weighted sum of 2D orthogonal basis function, which in our case is sinusoids. But this definition is valid for any transformation. We call about the wavelet. So the question is that what is the difference between Fourier domain and wavelet domain, or Fourier transform and wavelet transform? So see, it seems a bit difficult to understand, but it's not. Why? If you see this definition, it will get everything. Any function, any time domain or special function is decomposed into weighted sum of 2D orthogonal basis function. Right? Forget about the sinusoid in a manner similar to the 1D. So if this definition is valid for both, either Fourier transform or wavelet transform, the only difference is this basis function. Here we are using sinusoids. I think sinusoid signal, sine cosine. Okay, in wavelet we use wavelets. We decompose signal into wave. What is wavelet? Wavelet also has some frequency in this, but it only, for example, what is sine? Sine is this, right? Sine, will then you can make it cosine. Okay, and then say sine means cosine, sine. Okay, but what is wavelet? Wavelet is a small pulse that is present for this small system. Like say, okay, but since it still has some edges more prominent, it dies down quickly, very short pulse. Okay, so now wavelet transform and Fourier transform, is the only difference is this basis function. Like for example, I am decomposing any signal or image either into sum of sinusoids or sum of wavelets. So this is the difference, nothing else. Okay, so if you understand Fourier transform, you can understand wavelets easily. I said this is a very complex image, and I decompose into various components with some weight. But if let's say talk about very simple image like this one, so white means high, right, and black means low. So it means that if you imagine in 2D, it's like going to high to low, like high to low, right, like this. So this has just one frequency. So in the Fourier transform, this will be two impulses at the frequency of this signal. Here you see it's high frequency, so they are apart. Similarly, if you see these two signals, they have same frequency, but they have different phase, and this phase is represented here.
But how big it would be? Like imagine this the black. I want to take it to T and y-axis.
It's like no, zero is this white is what? One, and this is zero. So you are one, and then you are moving to zero because you're slowly moving. One and then shades means that you are going down to the black. So imagine it like the signal is just a signal, but this is a plane. Okay, I have another picture 3D. Yes, it's in 3D. Let's say okay. Let me try to plot this. Let's say if you have cos. Okay, so Fourier transform is two positive, both positive. But if you have sine, they are positive and negative. So if you remember, we discussed this definition about the discontinuous impulse response. We said this is 0 at all other location at t and infinity at equals to t. And by definition, this is again, if I take the integral, this is equal to 1 because this only exists at 0. And if I multiply any function with this, because it exists only at 0, it will give you the value of function at 0. And similarly, if you have shifted, you get that function, right? So the same definition, let's apply on the 2D, and we get this similar thing, but now we are considering a plane. Here it was just like 1D, now we have a whole plane, okay? What we have, x and t, when both are 0, you will get that impulse at that point, okay? No, here. Okay, and also if I take the integral like this one, so its integral should be 1 because it only exists at t and z equals to 0. Similarly, if I multiply any 2D function, in our case image, by this, so I get the location at this one. And similarly, shifted version is shifted version. So here we have some, you can note it down. If you want to, we have some definition. For example, not definitions, some representations. So this is spatial or time domain. Okay. So what it means that if I'm representing f of x, y, or f of x or f of y, this is representing discrete spatial domain. Okay, if it is f of t, z, this is continuous spatial time domain. This time domain will be 1D, spatial domain is 2D. Okay, this is clear. Please note it down because it might confuse. And then we have Fourier domain. Fourier. Okay, Fourier domain, right? So in Fourier domain, the discrete is represented by u and v. Okay, so if you have f of u, f of v means that this is discrete Fourier transform, DFT. If you have, and then you have a continuous. Okay, so for that you have mu, and write it like this, which is v, but different than this. To make sure that if you understand this, so it will be easy for you. So here, if you see, I am discussing continuous, right? So we have t and z. T in 1D, t z in 2D. Okay. Okay. Let's move forward. Now the same definition we have studied for the impulse response in continuous. Now we have impulse response in discrete. Now discrete I use x and y, and the definition is much simpler because this is 1 for x is equal to 0. Okay, and otherwise 0. And if I sum them up, I get 1. Previously we had integration, now we have summation, and then if I multiply these two, if only exists at x equal to 0, I get f of 0, and this exists on f equals f of x 0. Similarly here in 2D, the same definition goes to 2D, and this is the figure I was talking about. Let's say I'm saying delta of x minus x naught and y minus y naught, it will be represented like this. You can see this is a very good figure in 2D. Okay, and x naught and y naught cannot be same. Okay, it can be same, cannot be. Do you have any question, yes?
I think I can get out because when you talk about x and y, it's gonna be like a whole, like on the vertical axis, it's gonna be like a complete blanket.
It's a plane, we call it plane. Okay.
So we come down to only 1 point. And you multiply with the delta.
Let's get only that function.
1 point.
At that point. Let's say you have image multiplied by this, only get that value at that pixel value at that point.
So the whole domain,
Yes. Shifting this.
the whole domain is just 0. Just
Yes, yes, over. Okay. Okay, so now with this definition, also we have now the continuous Fourier transform, and but this definition will not be really used. We will go towards the discrete Fourier transform, so we will use that one. But anyhow, the difference is integral and summation. So in 1D, the Fourier transform of the time domain signal, which is t denoted by f of t, okay, taking the integral and multiplying with the exponential, gets you the Fourier transform, and the inverse of that will get you the time domain. So here we have just two variables instead of one variable, and we have two integrals and two exponentials. Okay, so is this clear? Just extension from 1D to 2D. Okay. Now the other thing that we discussed in 1D was what? After this we discussed sampling, and for the sampling we discussed impulse train. Okay. So what was impulse train? It was impulses. Okay. So let me go back and forth just to make sure that you know what I'm talking about. Impulse. This was impulse train, right? And the sampling we said this impulse train will be multiplied with this to get the samples. And we did side by side frequency domain. Why? Because we wanted to know which sampling frequency we have. Okay. So the same thing we have to do here. So here the impulse train will be in 2D. So we have now in x-axis and y-axis, like in whole plane, we have the impulses, and we can represent in this fashion, right? This is the impulse train in x and y direction both. Okay, because we are discussing the continuous, this is the continuous domain, so that's why we have t and z here, and these are the impulses in all domain with some separation, delta t and delta z. Here it was just different, but this is 3D visualization. But if I see from the top, I'll get this thing. So now, in order to discretize our image, I multiply this with the image. When I multiply, here what I did, I multiply this to get the sample signal, which is obvious. If I multiply the pulse train to the image, I get a discretized image. However, in frequency, what was happening? In the frequency, let's say the frequency transform of this was this, and the frequency transform we proved it of the impulse train was an impulse train with the distance equal to 1 by delta t in between, because they are inversely relationship, and also the height was 1 by delta t, right? So basically, if I'm multiplying here, what I'm doing? Convolution. Okay. So convolution also we proved it mathematically. The convolution is nothing but just putting this on the top of each of that. Let's do this for the image. Okay, so this is the impulse train, this is the top view, and if I take the Fourier transform, like in the 1D, I get again the impulse train with the distance 1 over delta z and 1 over delta t. Now the coordinates change from tz to mu v because we are in continuous domain for this Fourier transform, and from the top view I can see this. So this becomes this, yes? And this will also change, and in the Fourier domain, I can write expression like this, like 1D. You have pulse train with amplitude 1 by delta t delta z. This is here. Okay. Now I made the Fourier domain or impulse train. Now what I have to do, I have to convert this with image Fourier transform. So what do you think it will look like? What happened to the time domain? Yes. Yes. Okay, what happened here? This is Fourier transform of Fourier domain. So the convolution becomes this Fourier transform on the top of each of the impulse in the Fourier domain. This is what happened right here. Same thing will happen, but in a A, so 2D. Huh? So let's see what will happen to it. So let's say this is the Fourier transform of any image. Okay. So if I put this one on the top of each of the impulse, what I will get is this thing. It will replicate. although this is just shown like this.
Top view is what is this? Is this top view?
This is top view of the Fourier transform of the image. 1D, we have just to take care of the frequencies, left and right. But here I have to take care of the frequencies up and down, left and right both. Okay, so there are two different frequencies that I have to take care of in the sample. Now, see, so you get it right. Now, the thing is, in order not to mix it up like this, what I need to do, I need the samples to be placed such that each sample should be away from each other by 2 Vmax in V direction and in mu direction by 2 mu max. So I now have two sampling frequencies. Sampling frequency should be greater than 2 mu max in mu direction and V max in V direction. Yes or no? Okay. Okay. And if you do oversampling, make greater than, you can easily place them without intersecting with each other. And in order to get back, I will just take this one and then recover the signals, like the ones we did there. Remember that? Like this one. So I take a filter here to get back this. So this will give me the, if I take a inverse Fourier transform, I get what the signal is. So similarly here as well. And what the filter here should have the frequencies, the cutoff frequencies. The frequencies like these frequencies, and these frequencies should be half of the sampling frequency, whatever I suggested. Okay, it should be only the case. Even if it is whatever sampling frequency I take, these edges of the filter should be half of that. Okay. Half of the sampling frequency. Yes. In 1D, I think it's easy. This is cutoff frequency. So this frequency should be equal to half of the sampling frequency. Yes, the window, what is cutoff frequency, the maximum frequency here, okay, should be the half of this in order to recover the signal. With aliasing, without aliasing, whatever sampling frequency you have set, it should be half of that. Even if it is undersample or oversample, whatever. Okay, fine. And here you see this is an example of aliasing. If you have the sampling frequency is less than 2 mu max and 2 V max, so it will be some sort of aliasing. Okay, so this is the complete same process that we did. Here we set it in this fashion, this one. So this was the thing. The same thing. Let's see in the image domain. You have image, okay, and this is the Fourier transform of that image. Okay, so if I next what I did, I take samples of this, multiplying with the sample, so I get this thing. Okay, can you see the face or not? No. So what happened? Because taking the sample should you should see in the image, right? So why you cannot see the sample? Yeah, you can see the face, but still it's not there, right? Because the sampling I did not define it accordingly. But if I just switch it, okay, then you can see now clearly. Okay, if you go to the computer, you can see it in your computer. Maybe that.
What is it? Is that a smaller delta and this is bigger delta or something?
No, this is same thing. It's the whole sampling process. Okay, so this is image. I take the Fourier transform. I got this.
Okay.
Whole. Okay. Then what I did, like I did it here in the yes. So when I multiply, I get this thing, sampled version of this. Okay. Sampled version. So I took a sample. Yes. That because the sampling rate was not good. If I sampled it, it means that sampling means repeating this on the equal instances. Yes. Okay. Once I get this, so what I do, I should have a filter with cutoff frequencies equal to half of the sampling frequency in this and half of the sampling frequency in this. Once I get this and the others, all these multiplied by 0. So I get this and then I take inverse Fourier transform to get the image. And you can see the quality is not that good. And you can see some of the features are also not very clear. Okay. So if you see this, you see there are some loss effect. Okay. This is aliasing. Okay. Because of this, you're not seeing it. So very good. So is this clear? And this is again another case of aliasing. You have this image and you take the sampling frequency less than the neglect and you get aliasing. So aliasing you can see here. You see this one? And one of the way to reduce the aliasing also is to smooth it out. If you smooth it, you can get rid of the aliasing. No, it's even there we have it. You see this? But it's not prominent here, it's like prominent here. But you can see the design is also changed here. You see this? So this is what it is. Okay? Fine. If again because 1D we did sampling of the sampling, we get a signal that is in continuous domain. Okay, this is the Fourier transform, and this is again a continuous domain. You cannot store it. So what we need is the discrete Fourier transform. Okay, so what we are doing is in discrete Fourier transform, we take the discrete samples of the Fourier transform. Yes, remember that or not? Okay, so we did this, and then we said that okay, why not to go to discrete? There was a figure, yeah, here. So we said we can discretize this Fourier transform, and this is called the DFT. And since it is periodic, I can only take one time period. Okay, which is discretizing it into m samples, take the m samples, and if I take 2m samples, I'll get the replica of that. Or if I go from -m to +m, I'll get again the 2 replicas. It doesn't mean that I can just take these samples. This is enough. The definition of Fourier transform, now we have x because of discrete, and I move it to discrete in Fourier, so I represent it with the definition that I showed you. Okay, and this is a discrete Fourier transform with summation, multiplying with the exponential or sinusoids. Okay, and inverse will be just inverse with 1 over m. If I transform to 2D, I will have two summation from x and y axis. So x will be from 0 to m minus 1, y will be 0 to m n minus 1. So image was m by n size. Remember that? So same m and n. And then we have xy image, and we have the two variables exponential into them. Okay. So just extend it to 2. This is what we did. Okay, nothing special. Clear? And what is the difference? The distance, because now the whole one time period is being divided into m samples. So what is the distance between the two samples? One by m delta t and one by m delta z. Let's say I have m samples here, okay, and this distance is what? One by delta t. So if I have m samples in one by delta t, so what is the distance between the two samples? It will be one by m delta t. So in 2D we have two, m delta t and z delta t. So now, if you remember previously we called it the kernel of DFT, okay, like the kernel or the filter that we have. And why we call it kernel? It will be clear when we transform it to a matrix format. That is the way we did it one day. Okay, so now here is this separable function or not? Yes. It is a separable, very clear. Okay, so I can write this function as this. It means that the kernel of DFT is separable, and if that is separable, I can write this in this fashion, rearranging it, right? So what it means, what this function is doing, a Fourier transform in which direction? Y direction. So this is what we did. We are taking the Fourier transform, 1D Fourier transform along the y direction, and then after that, I'm taking the Fourier transform into the x direction. So basically, the 2D Fourier transform is nothing but taking the 1D transform along the y-axis like this, and then along the axis. If I had an image, I know that image has 0, 0 location here. So first, I will do the Fourier transform along the y direction. So if because you see the Fourier transform of f of xy is f of u v, right? So if I'm just doing along the y direction, I can call it f of xu because x is still there. V is transformed. This direction is being transformed, and then I do it on the column wise to get this. Okay, this is clear. Now, if you remember, I also tried to make the matrix format of that. You remember that? So this is very, I will say, if we can succeed in this thing, it is like computationally very efficient. Plus, it's also easy to compute instead of going into these equations. Okay. So what I did, this is for the kernel. This kernel is being denoted by Wm equals to e power minus j2 pi by m, right? And if that is the case, I can open the summation. After opening the summation for each u, I will calculate this. So for u of 0, I will get all these terms become 0. Okay, only you get f of 0, f of 1 to f of minus 1. So I can write in this here fashion, right? So f of 0 is 1, 1, 1. Apply this with this to get f of 0. Then for 1, I'll get, this will be again, this is 0, right? So this will become w1 and m, right? And similarly, so I get this point. So the same thing I can write in this fashion. Let's say I want to calculate a 2D Fourier transform, 2 point Fourier transform. So what I will do, what will be m here? M equals to 2. Okay, let's say I want to calculate the Fourier transform of, let's say, equals to 1 and 2. So how to calculate it? I have to calculate f of 0, right? And I have to calculate f of 1. Yes or no? So how to calculate like this? I need to find this matrix. So this matrix will be, the Wm will be actually W2 now because m equals to 2. And let's calculate it. So how it will be? 1 and 1. It will be 2 by 2 matrix, right? And then here also we have 1 because here 1. And then here we have W2, 1. What is W2, 1? I put it here, right? So if you have W2, 1 will be equal to e power minus 2 pi by 2. So j pi, right? And if I open it, it becomes cos pi minus j sin pi, right? And cos pi is 0, sin pi is 1. So it becomes, so you get the 2 by 2 matrix, you multiply with this one to get the Fourier. Yes? And these are different. For example, 2, 4, all this even, you will get very nicely shaped matrix, symmetric and very nicely shaped matrix. And for the odd, you will not get that good matrix. Okay, but it will be still nice. Okay, so what we have, the property of this matrix is inversion is not required. If you want to go back to the time domain, inversion of this is equal to the Hermitian conjugate, which means that we take the transpose and the conjugate of each term. Okay, so get it done. And also it has the property that the transpose of this is equal to the itself. So there is no need to take transposition. Okay. So let's move and try to do the same thing for 2D. So here what we did, we take the image, take the Fourier transform row wise and then go column wise. So 1D, okay, 1D Fourier transform, row and then column. So I can write it in this fashion. I take the f, Wn, because on the row wise it was n. Okay, so it was n by n matrix, the same W matrix, and here, then after that I take the 1D transform across the column. So in 2D, in order to calculate the Fourier transform, I can just first take this one and then take this one and I will get yes or no. Okay. Please, if you have any question, let me know. So this is an example of 4 by 4 matrix. In order to do the Fourier transform, I multiply this because this is 4 by 4. So we have x4 and y4. So W will be 4 by 4 in both directions. Okay. So W4, if I calculate, I get this thing. I multiply this from this side and then from this side. So I will get all this calculation. Okay. So now you can calculate, go back from there, and which makes sense. What is this image? We have just a constant number 1. Okay. So which frequency we have here? 0 frequency? Okay. Which frequency you see here? 0. 0. Okay. 0 frequency, right? DC component, because it's just one constant, right? So what you expect the Fourier transform to be? Yeah, so this is what we get, right? And just one. And just other is not there. It represents the whole energy in that image. That's why it's 16. Because it considers all the energies in this image.
So the image was like one at the other thing.
Just a white image, nothing else.
It's not like unity image.
Yes. Unity image is plain. Okay. So these equations, please try to make sense of it as well. So another thing that we did for the 1D was shifting. Why we did shifting? And we said, let's say this is discrete Fourier transform. This is the result of discrete Fourier transform. This is the result of the Fourier transform of the sample data, which is repeating. This is the Fourier transform of the 1D, and it's repeating here and here. And if I take a discrete Fourier transform, what I will get these sample, right? But however, the original image in this case will be look like what? Original Fourier transform in this case should look like this thing, okay? But if I take a discrete Fourier transform, I'm taking this sample, right? Yeah. So although this has the whole information that I have here, but it's not exactly the same shape as this. First, now, second thing here, you see this is zero frequency, right? So this is zero frequency. So this frequency is transform is across the zero or the DC component symmetrically. But here, if I take the DFT, it's not symmetric across the zero frequency. And zero frequencies are on the edges, or the low frequencies are on the edges. Okay. So for such reasons, and also I will say for the better visualization, what I do instead of taking this, I take the other half. So what I do, I just shift the frequency spectrum by m x to get the same shape as this. Okay, and this will be even clear when we do the image in the next. Okay, so what we do, first thing is the periodicity, as I mentioned, DFT is a periodic signal. So if I have the Fourier transform, if I move in any direction, let's say I only move in u direction by m points, where k1 is any integer, I'll get the same point at this. Or if I just move across v direction, okay, by n points, I'll get the same point back, right? And similarly, if I move in any direction, I'll get the same point. Yes or no? Okay. So what it means? Let me try to. Maybe I think you should have.
They are all identical. Wherever you go, they are same.
They are saying this is what happens. Let's say you have an image 1, 2, 3, 4. So basically, when I take the sampled version and take the Fourier transform of that, what I will get the copies of this. So I will get 1, 2, 3, 4, right? Similarly here 1, 2, 3, 4, 1, 2, 3, 4. Similarly here as well. Yes. So if I move wherever by the same points equal to m and I will get this same thing again and again. Yes. And this will so on. And so forth. Yes. So if I move n points, I get the same thing. If I move here, I get the same thing. If I move here, I get the same thing. So this is what periodicity is. So it's periodicity in the plane. Okay.
Okay, provided you take the right delta.
Yeah, that's why you have to move m or n direction. Fine. Now, in order to shift it, I have to shift by m units, right? So I have this property. If I want to shift the frequency, this shifting in frequency is equal to multiplication of the time domain or the spatial domain by an exponential by this amount. Okay. But here the shifting is by m or n, by 2. Okay. So if I put this, I should get this thing. Okay, if I put mu naught m, will be cancelled, and then will be cancelled, and this thing can be reduced to this one. Okay, this exponential. Okay, and you can prove it by opening it up and you call the sign term, and you will see that you will get this term. Why you get this term? You get it or not? I do it. Because here, what you get? E power j 2 pi x plus y. So this is 2 pi now. It depends 2 pi x. So x will be either 1 or 2. When it becomes even, get 1, and if it becomes odd, it becomes -1. So that's why I just wrote it in this fashion. Yes, all the sides. Okay, fine. So now, in order to shift it, what I do, I have to multiply image by this number and then take the Fourier transform. Instead of taking directly Fourier transform, if I take the directly Fourier transform, I will not get the centered spectrum. So I have to first do the shifting. I just multiply this, and I have an example for that. How to do this. Okay. And if I do this, the spectrum here will be shifted in the middle. Okay. Why it's necessary? In the next slide, I will show you. This is the original Fourier transform of the image without shifting. So what we have, high frequencies in the middle, low frequencies at the side. But I have to shift first. I have to do the shift. I get this thing, and in 2D it's making much more sense because see, the image for the single of filters are of low frequencies. So if I do this, it will still can make sense, no problem. But if I do this, makes much more sense because my centered image is of my interest, which is a low frequency component. This shifting will get you this thing, and this looks visualization. This is much better as compared to this one.
So I'm able to take this in previous one, you can take the Fourier transform unless I do shift.
Yeah, we are doing shifting, but it's indirectly in time domain. First, we have to multiply with this, and then take the Fourier transform, so it will give me the shifted version. Okay, not like taking first and shifting. No, it will be difficult. So first multiply. This is easy.
Okay, here if we do this shift in the frequency domain, then this same shift will reflect on the spatial domain.
This is what I told you. The shifting will be this. Okay, the shifting in frequency will be this. So the shifting actually when I'm saying shifting, I'm not shifting the frequency domain. In reality, I have to do this to make the shift happen. See what I'm saying? Okay, this is computationally much better because I just have to multiply with 1 or -1 depending on the value of x, or in 2D x plus 1. Okay, so this is much better as compared to shifting because if I do frequency domain then do shifting, it is difficult. Mathematically computationally inefficient. Okay, so you see you have a line, right? Okay, so what it means, this image is low frequency because you have just black and then you have just white. So it means that you have just one frequency which is low frequency here, one frequency, right? So you see, if I take that directly, you will not see it. Why you can see? Because if you see here, you see this here, these are the frequencies, which is not prominent. But if I do the FFT shift first, how to do FFT shifting by multiplying this with -1 x plus y and do the FFT, I get this. So this is much better visualization as compared to this one. Yes or no? Okay. And if I take the logarithmic transformation from your second or third lecture, so I will get even prominent just to make sure that I get some more prominency in the Fourier transform.
Now these two are the shifting.
This is the shifted, and this is the enhanced shifted. I just took the logarithmic transform from your first. Okay, so for example, this is the image, and this is the DFT of that image. Okay, so what it will give you? It will give you the low frequency on the edges. But I don't want that. I want it in the middle. So what I have to do is I have to multiply with -1 x plus y. What it means, each term I take, let's say this is 0, 0, right? An image 0, 0, 0, 1, 1, 0, 1, 1, right? So 0, 0, I put 0 and 0 becomes 1. So I have 1 here. Then this is 1, 0. So it becomes -1. I multiply with -1 becomes -2. Then similarly -3 and 4. Now I take the Fourier transform, I get this thing. Okay, so in this image, the frequency will be in the middle. Can we also do it in the Fourier domain? How the shifting occurs? Let's say this has the Fourier transform of this. What it means, it's repeating, right? It's repeating, right? So it means that I have to shift the Fourier transform. If I shift by u -1 and v -1, what I will get? Shift it by -1, I get this thing, right? And this thing is same as this thing. I'm trying to do like we shift in time. We do this to do shifting, but I'm just giving you another way that how it will be done here. Or in other words, let's say you want to be sure of your answer, how to measure that. No, that's not feasible. This is feasible because this is very easy. Just multiply with 1 or -1 for of them, right? But here you have to plot all this. Let's imagine you have u -3 or v -4 or something like that. So you have to plot all this to get to that point. But here it's easy. Just multiply with 1 or -. So easy is the time domain, especially.